It's my pleasure to introduce Fernando Garcia from the University of São Paulo. He'll be our second speaker of this workshop, and the title of his talk is there as you see, Spin, Excitations and Electronic Structure in the Barium Iron 2 Arsenic 2 family. So it's over to you.
Okay, thank you. Thank you for a nice introduction, and I'd like to thank the organizers for having me here, give me an opportunity to share this our work that we are doing at the University of São Paulo. Well, first outline of my seminar. So I'll be, let's say, revealing a little bit of the barium iron 2 arsenic 2 crystal electronic structure, and try to also bring out some open shoes, at least as I see as open shoes. And then I will talk specifically about phase diagrams and, of course, about some ideas that we had about this phase diagram and motivation for our work. And then I go through an outline of our investigation results. It's the usual thing that, some conference people like to bring up, results that are ready. But I actually rather prefer to use, instead of focus here in this paper, it's some of our recent results, I will simply flash a little bit here, trying to bring the main results and findings in this paper. And then I will go through actually this recent experiment results, which are actually will be open for discussion. So I think that by doing that, it can motivate a little bit more questions and so on. So hopefully we'll succeed in that. Okay, so of course, I'm not working alone. So these are my main collaborators. I highlight here, there are a lot of people, right? But I would like to, highlight this of these people here. Marli Cantarino, my PhD students. Most of the unpublished work that I'll be showing here, it's actually her PhD work. Álvaro Figueiredo, who's a former master's student in our group. Wagner Ribeiro, also a former master's student who's about to go to Europe. And of course, the people at Unicamp who's synthesizing the samples, and especially Professor Cris Adriano and Kevin BaFe2As2, who are here in their natural environment using all the gear for protection, for growing arsenides and so on. It's always something very dangerous. So as I said, a lot of people, when I say a lot, it's really a lot, because most of the results that I'll be showing here are synchrotron-based experiments. So, a lot of people need to be there, to put up all the instrumentation, so on and so forth. And of course, I have to thank our founding agents here. Okay, so in my perspective, the iron arsenide problem is a problem which relates to a certain duality of the description of the electronic structure. And here you have like the full structure of the barium iron 2 arsenic 2 material. But usually, to understand the electronic structure in this material, you have to look at, like, say, two building blocks here. So the first thing is that you have to look a little bit at the local electronic structure as determined by the iron tetrahedron. And here, when we describe this local electronic structure, we use concepts which are more, commonly found in discussion in chemistry and so on. So I call it the local electronic structure, which we usually assess by XAS experiments, right? But most of the time, we're devoting our efforts to understand what is the electronic band structure, which we assess via ARPAS. And we take all this complexity here of the crystal structure, and we let's say, abstract everything and put all this complexity, essentially describing, to describe this electronic structure by using 2 iron square unit cell. And I really highlight here the 2 iron stuff. And this is, of course, because when you are, because of the arsenic here, you have 2 irons in a square line, so they are not really equivalent. The arsenic has, a crystal field potential, which breaks the inverse symmetry of the iron site and makes your cell to be really a 2 iron unit cell. So here is like how you, of course, that these 2 electronic structures are somehow interrelated, and you can, of course, from very simple arguments, symmetry arguments, can have a cartoon of the electronic structure, something that I'm working with, but think a little bit about education, not actual research. But if we want to actually investigate the electronic structure, we have to look at that in more detail. So here reporting a little bit of the literature. So when we look at that in detail, we have to say that the ground state of the material is actually an antiferromagnet. So the electronic structure have like a high temperature electronic structure above the spin density wave transition and a low temperature one. So if we start with describing the high temperature one, you have this, again, to describe the electronic bands, we take this 2 iron square lattice here in cell. Because of their standing potential, you have something like this, right? And then you have to encode all the arsenic effect into, like say, the fact that the arsenic will select the relative energies of the ion orbitals and will actually determine which orbitals are indeed contributing to the ferrous surface. So these are the main orbital character of the banks close or at the ferrite level. And here's, let's say, a cartoon view of how this electronic structure goes. So you have this dxz, the yz, yz, and the xy orbitals contributing with hole pockets around the gamma point here. And here you see the ferrous surface. And contributing with electron pockets here around the M point as I stay here. Of course, this is a cartoon, and from the cartoon to the real electronic structure, or with the electronic structure that you can measure with experience, you have a long way to go. It's even with the best experience that you can do, best samples and best kind of instrumentation, you still have a lot of, it's not easy to see all the bands, to resolve the bands and the orbital character of the bands. But here it's a really good example for well-done work trying to understand in detail each aspect of the bands, right, when you perform the measurements. So, these are ARPS measurements which are being compared with tie binding models. And how you can see here, the experiments are comparing very well, and they are showing indeed the structure of the two hole pockets here, the two bands that will form hole pockets, and it's here being proposed that actually there is a third hole pocket which is comprised mainly by bands with dxy orbital character, right? And I'd like to call attention that in this paper, people are analyzing bands by looking at the so-called second derivative of the ARPS intensity. This is something that we usually do, but some authors prefer to take a look at more careful stuff like spectroscopic signatures, like you look at energy distribution functions and you fit it, and then you have, and then you can actually confirm the existence of a band. But it's quite fair to look at, like say, ARPS second derivatives and to infer the presence of all these spectral features here. So again, here's something which is more close to the gamma point. Here is more close to the so-called electron pockets at the XY directions. And of course, as I said, you have like an electronic structure above the spin density wave temperature and another below this one. And here is a comparison between the measurements in the normal state and measurements in the order states, again, for D-twin samples. And as you see, you can actually infer, again, existence of a lot of bands that crossing, but most of the bands now, you have even more bands than you had previously because of this phenomenon here, which is one of the key elements to understand the physics of the arsenide, which is the spin density wave folding. So usually if you go through a very simple exercise, you take, for instance, a square lattice, simply one orbital, right? And then, of course, we can solve that in a tie-bind model. But if you think of the existence of folding in this very simple model, you end up with a very complicated electronic structure. So here the problem is not just one orbit, one band, sorry, it's like 5 bands, and you have to consider that all these bands will actually fold, and this will, of course, give rise to a rather complicated pattern. So when you see here the proposed pattern, for the bands, and you compare experience, you don't observe that much of bands. Of course, it's not expected that you'll be able to observe all the bands because of the ARPS intensity selection rules and ARPS matrix elements. They have a very complicated dependence with the geometry experience, sample quality, and all kinds of stuff. So you can, of course, pinpoint some of the bands that you are expected to see. But there is another more fundamental issue here, which is, of course, the fact that in literature, you find that not everyone agrees with the spin density wave folding scenario, right? You might find the idea that instead of folding, the electronic structure of the low temperature of the low temperature region is not determined by folding, but actually by a complete reconstruction of the bands. This is something which is caused by the antiferromagnetic transition. So so in this paper here, they make a relatively good case for this type of interpretation. And one of the things that they are saying is that, well, look, it's very hard to see that much of bands, So if you do experiment with high resolution ARPS and so on, what you see is actually that the bands are more comparable with a scenario that compares really well if you don't think in terms of this spin density wave folding. In particular, if you look at the FEM surface features, you see that the symmetry of the electronic strakes are well described by this scenario where you're not actually thinking in terms of folding, but simply thinking in terms of the DFT calculation electronic structure of the ground state. So the point is, of course, that these authors here, they are being very conservative about the number of bands that they are observing. So instead of looking at second derivatives, they will look only at spectral features which can be clearly distinguished in their experience. So they end up saying, okay, we have less bands, right? So discussion is actually very important because when you see, let's say, when you talk about which energy scale is actually determining the electronic structure of the low temperature phase, maybe this is somehow related to the NXK, which is important also for the formation of the superconducting ground state. So I think that we have to keep this in mind as well. Okay, so this is electronic structure, right? So it's a tale about some hole pockets and electron pockets. Hole pockets at the center of the Brillouin zone, electron pockets at the corner of the Brillouin zone. And what happens, right? What kind of physics this complicated electronic structure will give rise? So here is kind of a cartoon phase diagram. And here's, let's say, in a nutshell, the kind of physics that you will actually observe. When you take the parent compound you dope with either electrons or holes, you will suppress the spin density wave phase, and then a superconducting dome will emerge. Of course, that more than a superconducting dome, you have this very interesting nematic order that we'll be listening in detail in a few minutes from Van Wilde. And this is a cartoon, and these are some examples for this cartoon. So for instance, here's an example of hole doping. Hole doping in the sense that you are substituting barium and put a little bit of potassium, which is one column behind the periodic table. So this is hole doping. And then you see the suppression of spin density wave and your superconducting dome. And here you see an example of electron doping with cobalt, right? And then you're seeing this kind of physics again. But it's quite surprising, and it's not included here, that actually you can make isoelectronic substitution. You just take out a little bit of arsenic and put phosphorus, and you see a phenomenology which is actually quite similar, right? But this type of cartoon actually hides a certain asymmetry of the of the phase diagram, which is the main motivation of my work. And this is the asymmetry. This is one of the examples of the asymmetry. If I dope my parent compound with cobalt, which is electron doping here, I get my superconducting dome. But when I do that with manganese, which is in the whole dope side, I don't get a superconducting dome. So it's not about electron or hole doping. It's really about the effect of transition metal substitution, right? It's not about electron hole doping, because if I just come back here, I can see an example of superconductivity in the presence of, caused by hole doping. And here, it's another thing entirely. So the idea, the point is that this type of asymmetry you observe for all transitional metals, I mean, which you can do hole doping, right? I mean, well, I take it back, but at least you can agree we can agree that you can observe for manganese and chromium substitution. So you're going to the hole dope side of the phase diagram, I mean, with doping, substituting with transition metals, but you won't observe superconductivity. So what is special about this type of substitution that precludes the formation of an SC state? And it's not hole doping, it's not the existence of local moments, because you have phases of arsenides, like the europium 122 arsenides, and they have very strong local moments, and superconductivity is there, right? So it's not that. So what is particular about that, and that's, let's say, trying to understand what is particular about that, it's our main motivation here. And of course, it's a long shot, but we believe that maybe if we understand why these phases don't have C, we can maybe understand why other phases have superconductivity. Okay, so we are going to break down this problem in two parts, actually. So the first part is we had to understand, or try to understand, which is the role of transition metal substitution. So this would be my first idea. And we have already a result. It's a published paper. I put some perspectives, and I show try to convince you that we have an idea what is the specific mechanism behind transition metal substitution. And then I will flash through here, but I will focus here on unpublished results. So I'm trying to motivate a little bit more questions, since it's really open for discussion, right? I try to, let's say, give my picture about that, and then let's see what I can get from the audience. Okay, so transition metal substitution was actually first addressed by XIS experiments. And the idea was very simple, is like if you are doping and you are changing the iron valence, you should see something in the iron K edge. This is clear in insulators, but that was not observed in the pnictides. So that was this idea that, what is actually happening. You have very, more recent, this in the early times, right? So you have a little bit more recent results showing that you actually have a tiny, this is XAS, and this is XES, I mean emission. So in emission, the spectral features are a little bit more narrow, so you can be more precise about what you're saying. And then people could see in this, in the 111 material, you can see a tiny change in the emission spectroscopy that you can actually do the electron counting and see that the iron valence is indeed changed, but by a very tiny amount. And it's not possible that this tiny amount is actually driving the whole type of physics. So since the early times, you have these two interesting papers here that put forward the idea that you don't have really doping in the sense that you're not actually adding electrons to the system, but you may as well tune the electronic structure by a periodic scattering effect. So it's more effect like a disorder, the effect of disorder that cause the loss of coherence of your stakes in the Fermi surface, and that will actually change the relative size of the pockets, and give rise to all this thing of create a mismatch in the nesting conditions, so on and so forth. We decided to look a little bit further in this, and we did we look at the XAS polarization dependent. to probe the anisotropy of the substitution effect. So the point is that you take a single crystal and you rotate a single crystal is equivalent to change the incoming light polarization. And when you do it, you have some extra selection rules to your XAS intensity. And we took samples here, right? We took a sample, cobalt doped sample in this part of the phase diagram and a manganese doped sample. So when we probed two complementary edges, right, in our absorption experience. We probed the iron K edge and the arsenic K edge. In the iron K edge, we focus our attention this A feature here, which is in the firm level. But there are two kind of bands or orbitals contributing to this feature, which are this local atomic hybridization, the iron 4p, iron 3d hybridization, and you have also the iron 4p, iron 3d hybrids orbitals. And this is, of course, due to the ligand field structure of the iron tetrahedron. But usually this one is a little bit more mystic, but it's allowed because of the lack of inversion symmetry. And the F feature here in the arsenic edge, you don't have this contribution. You have only, of course, the atomic transition is like arsenic 4p, but since this is a material, you have also contribution for the iron 3D. Okay, so what did you see? So what you see is that, like, we are assessing here the anisotropy. And by assessing the anisotropy, I mean I'm taking the intensity at a certain angle, and then I normalize all the intensities by the intensity at 0 angle here. And what I'm observing here is that the manganese has a very strong defect. When I dope manganese, I get a very strong effect, and almost no effect because of cobalt substitution. This is the iron K edge. When I go to the arsenic K edge, I still get a little bit of effect due to manganese, which we interpret somehow an increase in the localization of the states. But you see that the cobalt, almost it decreases a lot the anisotropy of the spectra in respect of with the parent compound, right? So interpreting these results, what we conclude is that manganese substitution mainly favors the localization of the bands, which in turn favors the localization of the iron-derived states. And when we take cobalt substitutions here, that cobalt substitution mainly increase the itinerant character of the arsenic iron bands, which in turn delocalize the iron-derived states. So our idea for the effects of transition metal substitution is pretty much the following, right? Since the iron lacks inverse symmetry, the hybridized states are possible. This is a fact. This is not part of our hypothesis. The arsenic 4p and the iron 4p does compete for the hybridization with the iron 3d states. I mean, there is an interplay between, the electron density in the iron will either hybridize with the arsenic or with the local iron 4p, right? So, our proposal is that this transition metal substitution tunes the arsenic 4p and iron 4p contribution, which returns to the localization itinerancy of the iron 3D states. This would be some sort of, let's say, chemical-oriented understanding of the doping process, right? Of course that, really? 7? Oh, sorry. But well, of course, that doesn't preclude all understanding this in terms of scattering and so on. This is chemical-oriented understanding that we believe that we can use that for design new superconductors. Okay. So now, understand a little bit the absence of superconductivity, talking about the spin excitations and electronic structure of manganese substituting by iron 2 arsenic 2. They have ARPAS. We did ARPAS and bricks of this type of materials. ARPAS is standard tool, everybody knows. But bricks is kind of, I'm putting here as an emerging tool, but it's more than 20 years old, but maybe not everybody heard about it. But I would like to highlight here the one thing that I can take a very tiny single crystal and I can do RICS, which is not possible with neutrons, for instance. Usually neutrons is a nightmare for experimentalists because I have to go really large samples, right? But one of the main disadvantage, which is simply because of instrumental limitation, is that RIX is limited to probe high energy excitations. So I cannot probe really close to Q equals 0. So this is, so far, kind of a limitation, but instrumental limitation. So I have here this results from 2019, and we learned that when we put a little bit of manganese, the excitations along the pi0 direction, which is supposed to be responsible for speculativeness, they are killed by the inclusion of manganese, right? They are killed in the sense that, we have a very strong dumping, which reduces the energy of these excitations when you go to the Brillouin zone border. So it's really something that caught attention. It was the first time that you could see composition dependence of the RIX signal. And it's kind of signaling that if you don't have these high energy excitations here, you don't have superconductivity. But we are left with some open questions. First, if manganese is tuned the electronic structure at all. We have some preliminary answers for that. Previous work and our own work, like just discussing this talk. And is the electronic structure determined evolution of ion-derived excitations? We first thought that probably no, but it would be worth taking a look at that. Well, so this is simply a review of the electronic structure. Focus here on directions, gamma to the electron hole pockets, right? So I'm really sorry. Okay, this is supposed to be the manganese doped sample. I don't know why it's chromium here, but anyway, anyhow, it's certainly the manganese result. It's in the paramagnetic phase, 150 Kelvin. So we did some ARPAs here. And you can see that the spectral features in ARPAs are actually something that you can understand based upon the parent compound. Oh, here, the 3 point, okay, so this is the parent compound. I'm really sorry, this is the parent compound. And this is, let's say, the 3.5 doped manganese compound. It's quite similar to the parent compound with some shifts of the bands as expected. Then we go to the 7.5%, and we can still see very sharp spectral features, which compare well with known models. We can calculate some features like the size of the pockets and firm level. We see that firm level changes, almost for nothing, right? So it's certainly not shifting the firm level. And what I can see here is that systematically, for measurements along quite distant directions, that the whole pockets are larger, right? But by a small amount. So something is tuning the size of the whole pockets, but this cannot be conciliated with that. It's not the shift of the firm energy which has changed the size of the whole pockets. And what's quite interesting to see is that these are, as I said, you can look at second derivatives, or you can actually fit a spectral feature. This is the result of fitting. So it's a very precise determination of the band position. And what you can see is that the bands with the XY character are actually changing quite a lot when you dope with manganese. The others are not changed that much, but the bands with XY character are changing. And these are precisely the bands which transitions with spin flips like XY, intraorbital character, are the situations that actually are connected to RIX. Okay, so, and the other one is kind of idea that you have when you look at the phase diagram. And here's my parent compound. You go to the manganese fully substituted sample, and you go from a 3D6 to a 3D5 guy and have some sort of Mott phase here determined by some other experiments. But here, when you go to the barium iron mature SN2, to the barium chrome mature SN2, you have here firm liquid, here you have firm liquid. But you see, somehow here in the middle of the way, you have a configuration which you can connect to this one. So what happens here? You have this preliminary study based on XAS, talking that actually, they're showing to us that actually maybe you're approaching a Mott phase here. So we decided to investigate that. First with RIX, and the sample that we had is this one, which is, oops, okay. So it's not really there, but it's approaching this half-half composition. And what we observe is almost a complete localization of the magnon excitations. The magnon excitations stop disperse when you go when you put quite a lot of chromium there. And the other thing which is quite interesting is that when you look at the binding chromium 2 or same 2 electronic structure, as previously did by this work here, we did it as well, and it had this very almost vertical bands here, and the firm surface, and they have this almost vertical bands here, and our firm surface is completely reconstructed by the antiferromagnetic transition of the material. This is the 100% chromium material, right? If we now go to the half-half composition, or not really half-half, but we are here, okay? What we start seeing is almost vertical bands again, and we are observing here this square-like firm surface feature, which are reminiscent of the, of the material in the other end of the compound. So it seems that when you really put a lot of chromium there, your electronic structure will have nothing to do with the parent compound, but will actually be under a complete reconstruction of the electronic structure because of the antiferromagnet state. So here are some of the main results of this last investigation. As I said, it's something which is in preparation. And my conclusions and outlook. Manganese it really helps superconductivity. So this is interesting because it destroys the moments, and at the same time it doesn't tune the electronic structure in the direction that you would like, right, to have superconductivity. And for lower chromium content, the magnetic excitations are most localized, and the electronic structure becomes similar to the case of the 100% substituted compound with complete reconstruction of the firm surface being observed. So that's it. Thank you.
Okay, thank you very much. Some questions? Yes.
Thanks, Fernando, for the talk. It's very nice. I was wondering why the DXY band are affected by the manganese. Why you have like manganese and chromium? Why don't you try? Have you tried the vanadium or something like that? Can you explain? Can you control like can you have some orbital selective mode transition?
Okay.
I have a lot of questions.
Okay.
Sorry.
Okay. Okay. Sorry. I'm not sleeping well because of my daughter, so okay. My head went away, right?
Why
so manganese? The manganese doping stuff. Okay. Which other one? Yeah. So this one, honestly, I don't know why. Right? I'm just, this is, the result is there, and it maybe could be some sort of more selective effect of substitution, right?
I see.
But I don't really, honestly, I don't know if I understand mod selective physics yet to be able to tell you that this is mod selective physics. But certainly, I can say that the doping affecting the bands distinguish between the band character, right? Okay. It's not the same for all the bands. And here it's quite clear that we are seeing that with manganese.
So I see. So do you have any comparison between the size of the pockets in relation with the calculations?
There are no calculations, at least I'm not aware for calculations, the effects of this kind of transition metal doping. I'm talking about this side of the phase diagram. Of course, for cobalt and so on, I have a lot of stuff, but I talk about small amounts of manganese and chromium.
I see. So
I don't even know what, like take a very simple calculation. You take the half-half material and you give me the DFT firm surface for that. We are trying to see if someone can do it or we have to do it ourselves.
Yeah, because I think the DFT is not enough in this case.
No, but even this starting point, I don't have. I would like to have, but...
More questions?
Okay, have you, do you know if there is a change on the, you have mentioned that the magnetic excitations are almost localized, but a change in the magnetic order when you dope a lot with holes? Because, well, we studied some time ago this range of doping. I don't remember exactly part of the details, but something that I expect is that the magnetic order changes from the pi 0, 0 pi, so this is stripe-like, to a pi pi standard anneal antiferromagnetism.
Yeah, you're right.
So,
I mean, if you compare the endpoints here, like just flash maybe too far. If you compare the endpoints here, you have like this is a Niel type of antiferromagnetism. This is simply spin-densed wave. So you change completely the symmetry when you go from here to here. And we are still here on this side, right? So the point is, yes, but the point, we are here probing the iron side. So these are the iron-derived excitations, right? So what we have here is a lattice that you have, like, say, spin-densed wave kind of order coexisting with the chromium fluctuations. Because you don't have a chromium order yet. I mean, no, you know. So it's pretty much like here, right? Because in the case of the manganese, here. In the case of the manganese, you have the same. But at this doping level here, you still don't have the order, the Niel order. What you have is like spin-densed wave order coexisting with the manganese fluctuations, which are of the Niel type, right? So we are trying to see if let's say, if the physics for chromium doping would be similar, because we are going the same direction of the phase diagram. So when I look here at this amount of chromium, you already have the order actually changed for this. Okay, so I have to ask for help of my students. Marli, do you know if here, which is the order here? I think did it change from spin-densed wave to Niel, or still have like a spin-densed wave? I see. I see. So yes. So I think that you got your answer. Here we are very close to this change in the order symmetry, right? So but the thing is that we are still only probing the ion-derived excitations. So what you're seeing is really the effect of having, you know, two types of interactions in the lattice with distinct symmetries, and you're seeing that the magnetic excitations in the iron cycles are.
Also because this is resonant in the iron edge. So everything you see is related to the iron, the Rick's experiments.
okay, but then is that even with the chromium, you see really very much the difference between the...
Yes. And actually, we are supposed to have all the way through, from small doping to large doping, but that's another problem. We are going to have it to the end of the year. But the physics will be very similar to the case of manganese. You start, you know, increasing the damping, then you go localizing the excitation until at this spot here, it's almost flat dispersion. So that's what you see. And it's quite interesting because it's even with a tiny amount of chromium, like 3% chromium, you start to see the localization of the iron-derived excitations. And it's really an effect of having two types of symmetries. Like you have spin-densed wave symmetry and the Niel type symmetry. I mean, why I'm saying that? It's, well, if I have more time.
1 minute.
Yeah, maybe 1 minute. Because if you look here, the chromium, this guy here, 3D4, and this 3D6 guy, they equally have S equal to spins, if you want this very localized description. When you go to the case of manganese, you have like S equal 2 or S equal 1, I mean, because of the fluctuation. But the manganese is really S equal 5/2. So it's completely different. You are adding two different stuff, different fluctuations, different type of spins. But here, no. The spins are, you know, they are kind of symmetric in the sense that, you know, the occupation is symmetric, but you are only changing the symmetry. And the symmetry is having this type of effect. You know, it's really continuously localizing the ion-derived excitation. Right.
Okay, I think because of time, we need to stop there and move on to the next speaker.
Okay,
so
thank you.
Fernando, again.
Thank you all.